Okay, so in this video, we are going to go into the Charles's law. Let me just write it down. Charles's law. Now, what this law establishes is the relationship between the volume and temperature at constant pressure and number of moles. All right, just important. Remember how guys, in the Boyle's law, we established the relationship between the pressure and volume at a constant temperature and number of moles. So now when the Charles's law now is now if you want to conduct studies, guys, using the Charles's law, so first of all, there's a relationship established between the volume and temperature, but also you have to keep in mind that you have to have a constant pressure and number of moles, guys, when you try to establish now this relationship. And so somewhere in your textbook, I've seen that they have this balloon here filled with room temperature. And then what they did next is that they poured on the balloon the liquid nitrogen. Usually when I teach this course and I have a laboratory experiment, what I usually do, I actually conduct this experiment where I bring the balloon in and I pour liquid nitrogen on the balloon. And so what happens next when you pour on this balloon now, it shrinks now. Oops, let me just actually draw the correct thing here. It actually shrinks now and becomes this small balloon now. So what is going on here now? Later on, once I'm finished, guys, with all of these gas laws, I'm going to go into the kinetic molecular theory, and I'm going to explain you guys the concepts behind each individual laws, why they behave the way they behave. Even though I do not see this explanation, guys, in your textbook, I will still go into this theory, kinetic molecular theory, guys, to explain you these different laws. So what happens now, the volume decreases. So what he was able, Charles, to establish a relationship between the volume and the temperature, and he realized that the temperature and the volume relationship is direct. In other words, if you in this case, decrease the temperature, volume goes down. But if you now let this balloon to come down to room temperature, you're going to recover the balloon with the same volume as it used to be. Okay, so in other words, now the temperature goes up, so does the volume. So the Charles's law establishing the relationship between the volume and temperature, and it is, guys, a direct relationship. Now, what kind of problems now could be now you would be solving here is if you change, for example, the volume, increase the volume, and so will be the temperature increases, guys, because you still have to now, the ratio between the volume and temperature has to be the constant value. And so if you increase the volume, this has to go up in value so that you can still, the ratio will be still the same or equal to the same constant. Now, if you now decrease the value or decrease the temperature, the value will get decreased so that, again, the ratio will be here kept constant. And that's pretty much, that's the problems, guys, you're going to face. They're going to be V1, T1, V1 divided by T1, of course. Let me just make this correction. T1 is equal to V2 over T2. And so generally, guys, you'll be given now 3 out of the 4 terms. And you will have to figure it out, guys. The 4th term that will be unknown. And we use, guys, rules of algebra to figure it out. It will be cross multiplication, of course, down here. So let me guys, pose a problem here for you. Let's say that, let me just maybe get into your textbook and solve a problem, example problem in the textbook. So let me just, there you go. So I got example 12.4. Example 12.4, that's page 500 here. All right, let's take a look at the problem. So a helium-filled birthday balloon has a volume, so they're giving you V1 in here, 223 ml. And then the temperature, now, guys, very important. They give you temperature now, Celsius here. But the temperature, anytime you guys do the gas laws, it's always Kelvin, always Kelvin. And we're going to talk about the Kelvin in a moment, how this scale was actually how the scale was discovered. So we're going to talk about it in a moment. So they say 24 degrees Celsius. We're going to add 273.15 to convert it to Kelvin. Again, this is technically not a correct conversion. You really should have multiplied by 1 degree Celsius in the bottom to cancel. On top 1 Kelvin plus 273 Kelvin. I just do the shortcut in here. And then the balloon is placed in the car overnight during the winter where the temperature drops to, there you go. So they gave me the T2, and that looks like a minus 13 degrees Celsius. And apparently what they want me guys to figure it out, which I will in a moment, they want me to figure out the volume now of this balloon once the temperature drops. And again, we can conceptually now, there's a direct relationship. Now, if temperature drops, so will be the volume now lower to keep that ratio constant. Now, so again, so initial volume 223 ml. And so what's going to happen here now, 223, now it has to drop because temperature dropped. So let's see how it works. So V1 over T1 is equal to V2 over T2. Okay, now I need the V2, so the V2 will be equal to V1 times T2 over T1, cross multiplication. I want to bring this one up. This one is by itself to leave it, right? So the V2 now will be equal to, now V1 is 223 ml times the T2 now will be plus 273.15. So that will be, looks like 260. Now again, because this one here is in the ones, we're adding here, so we will have to run it off to the ones in here, so this will be significant here. I'm going to just put the dot in here. 273.15 minus 13 looks like 260 Kelvin. And now we will divide now this by 24 plus 273. That looks like 297 Kelvin. All right, let me just verify that this is correct. So 20 plus 70, it's 90. 297, correct. 297 Kelvin. Kelvin, guys, cancels out. Well, now we get the correct units here. I'm going to use my calculator now, conduct the final calculation here. So let me just plug things in. Now, let me just do it real quick, guys. So it's going to be 223 times 260 divided by 297. And so the final answer is 195 milliliter. And again, guys, we predicted that the volume will drop to the low volume. And so that actually, that is consistent with our prediction here. Now, so what's another importance, guys, of the Charles's law? So when William Thomson, better known as the Lord Kelvin, conducted numerous experiments using now Charles's law. Let me just erase a couple of things in here to make some space here. So what he discovered is that all of these graphs where volume versus, guys, the temperature. Let me just draw this now. So he's got this, let's say, here we got volume liters of the gas in liters, and here we got temperature in Celsius. Temperature Celsius. So he studied all of these gases at different pressures, and again, each graph represents different pressure, but it's a constant pressure here. So let's say some P1, let's say some now some P2, now let's say some P3. And so when he now extrapolated these graphs, what was interesting about now this, they all got extrapolated into just one point. So he did experiment, guys, at many different pressure with different gases, and he still got the same result. So the significance he recognized of this is that any matter can achieve, you cannot go lower below 273.15 degrees Celsius. So what he did, he chose this as a 0 point, he made it 0 Kelvin, and he created now this temperature scale that he called now the absolute temperature scale that uses now the 0 Kelvin is the lowest temperature, guys, that is attainable by any kind of matter, guys, in the universe. So in other words, you cannot really go, and if you guys go into the physics books, they actually explain it a much better way with greater details. But just want to, guys, emphasize here that the 0 degree Kelvin, nothing can actually get to this temperature. But this is just a theoretical temperature of 0 degrees. This is the lowest temperature possible that could be achieved by any matter in the universe. But if you guys again go into the physics books and actually start learning about this, this thermodynamics process, you will realize that well, nothing can be actually can achieve the 0 degree Kelvin. It's like a limit, and limit going to 0. And although nowadays using lasers, the temperature is kind of, we're getting there. It's like 0.0000 something to something. I don't guys remember exact numbers, but you can look them up. So we're getting close to the 0 degree Kelvin, but we'll never be able to achieve 0 degree Kelvin. So this is what he realized was the lowest possible temperature achievable in this universe. And so he made it now absolute scale here, where 0 degree Kelvin will be the lowest possible temperature. And remember, guys, so now the Celsius has been offset by negative 273.15 Celsius, guys. So that would be now 0 degree Kelvin equivalent to. And so if you guys remember our, one of the first lectures, you guys realized that I actually derived the conversion between the Celsius and Kelvin using the difference in I guess the difference in melting and the boiling point of water. And I was able to convert now degrees Celsius into the Kelvin, because there was just a difference. The magnitude of Celsius degree is equal to, of course, degree Kelvin, but the offset was 0 here because the 0 Kelvin was equivalent to negative 273.15. And remember, guys, how I was able to go from Celsius to the Kelvin, was able to adjust now for the difference in the 0. And so that's pretty much, guys, what the Charles' law is. And again, the problems here are pretty much the same. You're given 3 out of the 4 terms, and then you will have to find the 4th term. And it's just the sheer algebra here to figure out the final answer. So I'll see you guys in the next video. I'm going to go into the Gay-Lussac's law, and I will also go, guys, in kinetic molecular theory, explain you guys these laws. So I'll see you guys in the next video.